list, right? List of hyperlinks. We all know hyperlink is you click on it and you go. So anything you Google out, you get a list of links to websites, correct? So when you search, how does it go? Usually you click on the first link and you hope you'll get what you're looking for. Otherwise you go to the next and the next and the next, right? It's sort of more obvious when you click on a big screen, a laptop or something, but even on the phone, when you reach the end, you say next, and then you get one more list, and then you say next, and you can keep on going. So, you all have searched many, many times what you need, what you had in mind. Most of the times, it's within the first 5, sometimes within the first 2, 3 only, right? So, how does this happen? Like the relevance, what you're looking for, and what you're looking for that say Haar wavelets, that may be there in hundreds of sites, right? A lot of people may have worked on it. But most of the times, you get what you want right in the top few. So how does this happen? There's something called a Google PageRank algorithm. Anyone has heard of it? Okay. So this algorithm was developed by a maths graduate and a computer science graduate. These two from Stanford University. They use just undergraduate maths. Really, you'll see how simple it is. And now you know where Google is such a multi-billion, I don't know, though I'm a mathematician, after a few zeros, it all seems like infinity when it comes to money. So they're such a big organization. So how did that, they started off in a garage. You might have heard that story. So with just some undergraduate maths, how did they do this? So let us first see what they did. So what are the fields of our undergraduate course which they used? First, they used linear algebra, basic eigenvalues, eigenvectors, that part. Second thing they used is very basic graph theory. Third thing, some Markov chains. Just a beautiful integration of these 3 topics, and they came up with the Google PageRank algorithm. So, just next slide. Okay. So now, when first, like I think you are all very young, but some of us here, we are used to we have seen pre-Google days. Can you hear me at the back? Okay. Before Google came, there was Yahoo, there were other search engines, and most of them had like whatever keyword you're looking for, many occurrences. The page which had lot of occurrences of that was given high rank. And where a page has low occurrence of that was given low rank. That's the very first step kind of algorithm it was. So what happened with that? Say I want, I'll use the example Haar wavelets. I'm searching for that. What I'll do, I'll make a website. I'll have just 10,000 occurrences of Haar wavelet and nothing else. By this old algorithm, what will happen? This page, which contains practically no information, will be first on the rank. So obviously, it's not a good algorithm to just do word count. So now, okay, many of you are research scholars. How do you know that your paper is good? How does it work? We say we publish in a good journal, right? If I got my research paper published in a good journal, it's good. And if not so good journal, then it's not so good. How do we know that that journal is good? Because good journals get published in it, right? So this way, how do we know that a particular website is good or not good? It's by those who have referred to that website. Just next slide. Next slide. Okay, these are the previous slide. Yeah. No, next, yeah. Next. Okay. So there are two things in judging which page is good, right? You want to, the objective is what? To give ranks to the website. This is the first rank, second rank, third rank. For my search, which are the ranks? So what do you first do? You have to rank these pages. How do you do it? Not just by number of word occurrences. You see how many how many websites have referred to this website. If lot of websites have hyperlinks to this website, then it must be an authority website, right? So, next. See, now the web pages, presently there are billions, right? Websites itself. So we won't go into billions, we'll just take a small universe with just 4 websites. And these arrows are, if website 1 has a hyperlink to website 2, then you can see that arrow. Does 2 have a hyperlink to 1? It doesn't have. So let's consider the small universe of only 4 websites, and each hyperlink is an arrow, right? Now, so any click, if you click, you go, let's simplify it. Any click means you go from one website to another website. So you can think of this as a Markov process. You've studied Markov processes, correct? You're familiar with Markov processes? Okay. Okay, then there's another approach to it. Just a next. Okay, let's take a graph theory approach to it. Can you see this as a graph? You can see it easily like a graph. Out degree means there's a link from your current website to the next site. In degree means some other website has a link to your website, right? Next. So, next. So, okay, stop there. So this, our transition matrix, if this was how the graph was, we have an adjacency matrix. Think a graph can easily be modeled as a matrix. Can you see it? Have you seen these before? How a graph can be just equivalently represented as a matrix. If from, you write node here, see there, node 1, 2, 3, 4. So I've written the columns. Now see, 1, 2, 3, 4 is there. Node 1 has in degree 3. All 4, 2, 3 and 4 have edges coming into 1. So there are non-zero elements on the columns. This is column stochastic for those who know. Okay. So it has all ones. 1 means it is incoming. Column 1, all the incomings are non-zero. Column 2, if you see, it is regarding the in degrees of website 2. So website 2 has in links from 1. Website 2 has from 1 only. From 3 to 1. Okay, website 2 has from, is that only from 1 it has. How come? From 3 and from 4 it should have. Oh, okay. Okay. I'll see what was right. I don't know. Anyway, website, according to the in degree, you fill in those numbers, right? Next, now see website 3. Forget that graph. It's right. I can't figure what happened right now. But anyway, see website 3. From 3, which are the outgoing edges? Outgoing only to 1, right? So 3 has all its recommendations. Who has 3 recommended? Only 1, not recommended the others. So it's like whatever recommendation 3 has given, it's entirely given to 1. So in the 3 column, 1 has the whole proportion of recommendation, full, 100%. Instead of writing 100%, I'm writing 1. So that's the column. Now if you see column 4, what is the out degree of 4? It has gone to 3 and also to 1. So 3 and 1, the out degree is 2 out degrees. My 100%, I'm dividing into 2 parts. So 50%, 50%, you have the out degrees. It's not in degrees, it's out degrees. So now 2 also falls in place, right? 2, what is the out degree of 2? It goes to 3 and to 4. So 3 and 4, your importance, total 100% importance, has been divided into 2 parts, 1 to 3 and 1 to 4. So this is called a transition matrix. How I am moving from one state to the other state. There are only 4 in my small universe. With that, I can completely do away with the graph and equivalent representation in a matrix form. You see that? You've studied matrices like this? Of course you have. This is a weighted graph, right? With costs for each edges, right? You've studied a lot about these kind of graphs. So now you have a matrix. Do you see anything about the matrix, the columns? What can you say about the columns of these matrix? Do you notice any pattern? Column 1, column 2, column 3, column 4? Correct? The sum is 1. So from every website is sort of transferring it has to, in the next click, we are assuming that it will leave that website and go to some other of the other 3 websites with 100% probability, that is 1, probability 1. If it goes to 2, we assume that it's equally likely to go to any of the 2 and put half-half. Correct? So now, how important a page is. Note, all this we are doing, all this work we are doing to give ranks to the pages, importance. How important is a page? If lot of pages refer to it, have hyperlinks to it, then it's important. And also, it's not just the number, it's the quality of websites recommending it, right? Just because, okay, if there are 5 people saying, oh, so-and-so is very good, right, is something. Like if Einstein comes and says you're very good, only one person said, is it the same weight? No, right? It depends who recommends also, right? So the first point is number of links pointing to it, and the second point, importance of each link. So it depends on the importance of the page it is from which page it got a recommendation. So these 2 concepts have to be modeled into our graph. We saw the graph and we saw the equivalent matrix. Great. But then how is this point being modeled in? Okay. Now let us take, we all like equations. Let x1, x2, x3, x4 be importance of the 4 pages, right? x1 is the rank of first page, x2 is the rank, second page should get x3, x4, so on. So we'll say, let us give the ranks, the importance weightage, instead of calling it ranks, let us say the weights for page 1, page 2, page 3, page 4. How did page 1 get its importance? Can you go to a slide earlier? This transition matrix, I think I put a slide after that, I didn't know I wouldn't have that thing in my hand. I'll just see. I want the transition matrix and the, okay, this is, go back. Yeah, okay. Now, there was there was a hyperlink from 3 and from 4. Just, I'll explain the first equation, remaining, I'm sure we all can just deduce. There was a hyperlink from 3 to 1. There was a hyperlink from 4 to 1, right? But 3 was such that it didn't have any hyperlink to any other. It gave all its importance to x1. Whereas 4, it recommended 2 websites. So from 4, you get a website 1 gets only half the importance. You see how you got the importance equations? So these 4, you get these 4 equations. Each x1, x2, x3, x4 are the weights for each page, right? Now, how do you solve this? I'm sure you can solve 4 equations, 4 unknowns. Next. We mathematicians, we'll smartly make it into a matrix equation, right? Now, just go. So this is a vector, x1, x2, x3, x4. This is a matrix A, and into x1, x2, x3, x4. So what does this look like? What does this look like? Ax is lambda x. Does it ring a bell? Eigenvalue. What would the eigenvalue be? This is not, we usually write what is on the right on the left, what is on the left on the right. So let this matrix be A. Let the vectors be x. Next slide. So what was in the previous side is x is equal to ax. But we are more comfortable with ax is equal to x, or ax is 1x, right? So how will we find x? You have to find the eigenvector corresponding to the eigenvalue 1, right? So the whole problem of finding ranks for pages has been just made what? You make it, I'm saying it in a very simplistic manner. Of course, there are lots of things to consider, but very basic idea is what? Represent the website as a graph. Second, forget the graph so that you can make it a transition matrix, it is called. From which state to which state it's going, all the column sums are 1. Next, just see it as a set of linear equations. Next, you just find the eigenvector corresponding to the eigenvalue 1, right? Okay, this all seems very nice, but what is the dimension of A? 1 billion websites, so 1 billion by billion. Billion is 1 followed by how many zeros? Million is 6 zeros, billion is 9 zeros. So see the type of numbers we are dealing with. No Python, no C++ can deal with that. So now the thing is how to compute. The good news is, what kind of matrix will it be? Lots of entries or sparse? Sparse means lots of zeros will be there or everything will have entries. What do you think? When is a non-zero value there? When there's a link from website A to website B, right? So any website maximum, how many, what will be its out degree? 5, 10, maximum 100, not more than that. But there are 1 billion websites, so most of the entries are zero. So that fact is used, such algorithms will used, which work well on sparse matrix. The word is sparse matrix for matrices which are very large, but lot of zeros in. So next slide. Okay, so now, how do we find the eigenvector corresponding to the eigenvalue 1? Now that is not easy. It's easy with 4, 5, 10, 100, okay. But such big matrix, how to find? So we do some cheating. There's this theorem. Okay, I think everybody knows this, what's eigenvector, eigenvalues. Engineers need this kind of intro. Mathematicians don't. Next. But this result, I don't know whether students know or don't know. Especially the last one, it's interesting. For any matrix A, any nice matrix, nice means I'm meaning with real number entries. Any nice matrix A, every eigenvalue satisfies this. Minimum of the row sum, column sum, every lambda, every eigenvalue is less than that. So you get a upper bound. Rather, you get a lower bound. Is that upper or lower? What kind of bound you get? Yeah, you get a max. It can be maximum what? The minimum of max row min sum. So you got a upper bound. It can't be more than the minimum of the so what will be the upper bound for this? Tell me. Column sums. 1. So lambda will be maximum 1. Now, is one eigenvector? Is one eigenvalue? How do you check? Now, just this matrix which was there. Can you go to the slide which has, no, that one, yeah. Down. That matrix, where 2 were there. Pakka eradittala. Just go up. Yeah, this is also fine. Yeah, this is fine. See this matrix. Now, imagine its transpose. Imagine its transpose. You can write it down, those of you who are like energetic even at 3 p.m. You can write it down. What will be its transpose? You can say, and now take 1, 1, 1, 1, the vector with 4 ones. Multiply it. Will you get 1 back? Right? You'll get that back. So what does that prove? 1 is an eigenvalue and 1, 1, 1, 1 is an eigenvector corresponding. But you'll say, ma'am, you talk for the transpose. What about the original? Right? But eigenvalues are the same. A matrix and its transpose both have the same eigenvalues. Eigenvectors may be different, but eigenvalues are the same. So 1 is a eigenvalue for this matrix. And we know from that result, that max upper bound, that it can't be more than 1. And 1 is an eigenvalue. So you have found that 1 is the largest eigenvalue. Right? Now, again, what things, have you studied Rayleigh's power method? Okay, that's a method which, it's an iterative method which calculates the largest eigenvalue. Other values may be difficult to calculate, but it's a neat one. Next. So you have the Rayleigh's power. Have you studied stationary distributions, Markov processes? So either way, both point to the same result. That's the sort of beauty. Whether you look at into it as a Markov chain, or you look into it as a finding the largest eigenvalue. Both will give the same thing. Next one, next one. Okay, we'll come back to this if we have time. Just go to the last. Yeah. There's a series of matrices. Yeah. Next slide. No, I can tell you the slide number. How much time do I have? 5 minutes? No, if it's 5 minutes, I have. Okay. So, yeah, that 24. 24. This is the, yeah, just can you make. So, this is, you start with the initial vector V, which says all are equally likely to start with. Then A is our matrix, transition matrix, you apply it. That is where I will be after one click. That is A. That's a Markov chain. It's nice, interesting. Read it. A square V is where I will be if I take 2 clicks. And then, and so on. A5 is after 5 clicks. After, as you can see that it's converging? So you get these values. So that is x1, x2, x3, x4. x1's weight came to 0.38, 38%. So your whole weightage you have divided into 4, not all equal, not equal. First one got lot of weight. Second one, which is the first most weight, most important was website 1, which is the next most important website? 3, and then next 4, and last 2. So if you go back to that site, you can try to figure out why. It may or may not be intuitive. Just see if you had already guessed that. Try it with different websites. So the slides have more if there are loopholes and things. If the graph is a graph theory, those who are studying, is it strongly connected? We can apply these results if they're strongly connected. If it is not, what to do to make what assumption? You put a damping factor. Like we have assumed that with one click you go only to the random walker, the surfer, clicks only to hyperlinks which are there on this site. But that doesn't model reality, right? You may go to a site which doesn't have next. Instead of only following the hyperlink, you can go to some other site. So you can have a damping factor, that is every other site in the universe, there is a non-zero chance that you can go there. So those technicalities are there. And right now, this was a proprietary algorithm. Only 5-6 years back, it came into, like it's now, there's no secret about it. Of course, published paper was there, but actual implementation and all, only last 5-6 years it's public. Do I have time? Yeah, so Google rank, now you see it just doesn't depend on these things. What else does it depend on? When you search, what else? When you search, what else does it depend on other than page rank? Okay, you see it depends on your history also. What you have searched, it depends on your location, many things. So all this needs a lot of mathematical modeling. So in fact, all these Google and all these industries employ a lot of mathematicians. So you can think of that as a career. I think I'm exceeding my time. I'll stop now. I just hope I've conveyed that all what we are learning, even in undergraduate, has so much potential for application to real world problems. I think I'll stop now.
Any questions?
Yeah, any questions you can.
So I would like to thank Professor Sarayu. Yeah, there is one question. You can ask.
Hello. My name is Manoj B from second year MSc. Fascinating lecture, Professor, but I have some questions. Well, you do have said about the transition matrix, how it related to the graphical representations. Well, when we take a determinant in a R power n Euclidean space in linear algebra, it represents, for a square matrix, it represents the area under the matrix, the vectors. It has been after transposition. So what does that means taking a determinant in this?
You're not taking any determinant.
Okay,
It's just the matrix and eigenvalue.
okay,
Since you're asking, eigenvalues are usually not usually, are always the sum of the diagonals. Right? You know that
Yeah.
result. So here you have the sum of the diagonals will be your sum of the eigenvalues will be the sum of the diagonals. But you already, that result is not so useful here because you are interested only in the eigenvector which corresponds to eigenvalue 1. So we are not taking any determinant anywhere.
no, I mean like, what if we take determinant? What could that number
What could
means?
it mean?
Mean to for this transition matrix, for this graphical representation, what it can represent?
Right now, off the shelf, I really can't say anything, but it's a good question. Why don't you think about it?
Yeah, yeah. I have another question also. So in that same Euclidean space, when we apply the transformation, something like
You don't have to generalize so much
Yeah.
to Euclidean space. It's a very small thing
Yeah.
set. Yeah, finish your question.
yeah, like for a power k belongs to n. When you apply the transformation again and again, the all
Which
the points.
transformation are you talking about? That
In
A
general,
power,
in a linear algebra, general, consider R power n to R power n. So in that space, when you apply the transformation for all the points in the Cartesian plane, it going to converge to the eigenvector of applying the same transformation again and again and again. So same question. I mean, like, what that could imply to this graphical representation, this diagram?
Yeah, so the
Taking the repetition, yeah.
graphical representation of eigenvalue, eigenvector is, eigenvector is that vector which does not change its direction under
Yeah.
that matrix operation, right? So this will be, this matrix you have to find, and here eigenvalue is 1. So there's no magnification, either enlarging or diminishing.
Yeah.
It all stays the same. But there's no real, I cannot think of any application of this geometric concept to
The graphical transformation,
of,
yeah.
finding the weights, how
Okay.
the weights are. If there is, I'm sure it will be a good thing to work on.
Yeah,
that's,
I will
that's
say about
really correct way to think.
Yeah,
Now-
I will say about it, ma'am.
Yeah.
Thank you.
Any? Yes.
Here, so we have to compute powers of A.
Yeah.
Whenever the matrix A is large, billion, then explicitly computation of powers of A is taking place behind the.
No,
S.
that's why we use Rayleigh's power method. And using the fact that it's a sparse matrix,
Okay.
there are algorithms
Yes.
which will make it simpler. Because it's a sparse matrix, it's possible.
Well,
Even then, that's what Google is doing in the background. Of course, you'll need a lot of processing
We have to
power,
s-
even though it's sparse.
We have to skip the wherever the zeros multiplication.
Yeah, there are
Is there an alternate-
optimizations.
Yes,
There
is
are
there any alternate method to explicitly compute? It will avoid the computation of powers of A whenever A is sparse.
powers of A
Yeah.
is the easiest way. Otherwise, you
Because-
have to solve it.
Yes,
That
yes.
is mind-bogglingly difficult to solve. But powers of A is doable.
Even whenever A is billion size, whenever you click Harviolet, it with a fraction of second will give the.
It's done,
yes.
pre-done. It's pre-done.
Means I think is it taking place back end all the
No,
powers
it's-
of
they already have it done. There are things called web crawlers which are doing it all the time.
Okay.
And it is importance of websites is put.
Okay.
Then when you put the site, it is a weighted average of many things like importance of the page, best page among that, plus your location, your history, all that weighted average will give you the final what comes to your screen.
Okay. Thank you. Thank you.
Thanks.
I would like to thank Professor Sarayu ma'am for the wonderful talk, and it is totally something new in this the 2 days of conference. Totally new idea, something new what our students should know, and it gives you to think about the opportunity outside, right? Because as ma'am said, for mathematicians there are a lot of opportunities outside, but you have to think in right direction. Only if you just think in the course, whatever is theorems and all, if you are thinking, that is not sufficient. You have to think about the application of that, okay? And as ma'am said, it is Markov chain that is comes under actually statistics, this one, but statistics paper is not there as a part of optional, like elective paper it is there. So I'd like to thank ma'am once again. On behalf of the organizing committee, I would like to invite Professor Padmanabh Reddy sir to hand over the mementos as a token of gratitude. Thank you, sir. Actually, there are one online session is going on. So, by Professor Ismail Nachi Kangul from Turkey, and one more online session will be by Professor Shiv Shankar Das from BHU, Banaras Hindu University. The links are shared in the group. So those who are interested, you can say go to a comfortable place. Maybe here there is no network, so you can go to a comfortable place and you can just listen to the talk what is going on. And after that 4 o'clock, so 4 o'clock you should be back here for the valedictory session. There will be 4 to 4:30, half an hour valedictory session will be there. You all should come back and assemble here. Okay? Thank you one and all.